Imagine digging in your backyard, maybe planting a tree, and your shovel just clinks against something hard, metallic. You dig a little more, heart pounding it, and suddenly you unearth this lost treasure chest, just overflowing with gleaming gold. I mean, the thrill, right? The surprise, the sheer value. But okay, let's unpack this a bit. What if the real treasures we rely on every single day aren't just gold? What if it's the lightweight aluminum in our planes, or the miles and miles of copper in our electrical wires, or maybe the colossal iron structures holding up our bridges? These everyday elements are, well, they're just as precious, really, and often far more challenging to find and then extract and then transform for us to actually use. Welcome to the deep dive. This is where we take a whole stack of information, could be articles, research papers, our own notes, and we try to distill it all down into the most important nuggets of knowledge for you. Today, we're diving deep into a really fascinating chapter from chemistry, the molecular nature of matter and change. Our mission for you today, it's simple. Give you a shortcut to being truly well-informed about the very foundation of our material world. We'll explore how these elements occur in nature, how they cycle through the environment, and how we as humans painstakingly extract and transform them. Get ready for some serious aha moments, and you won't need a single visual to follow along.
Absolutely. And it's not just about, rocks and digging stuff up. What's truly remarkable here, I think, is that this is really a story of Earth's own evolution and the incredible influence life itself has had on chemistry, plus human ingenuity applying fundamental chemical principles, things like kinetics, which is about reaction rates, or thermodynamics, energy changes.
The core chemistry concept.
Exactly. Applying those to actually harness these resources. We'll connect the dots, basically, from deep inside the Earth right to the products you hold in your hand. It should give you a really solid understanding of the chemistry behind our whole material world.
Okay, sounds great. So let's begin our journey by looking at Earth's elemental treasure chest. How are elements actually found out there? So picture our planet forming, about 4.5 billion years ago. Initially just this swirling molten mass. Yeah. But as it cooled, something really remarkable happened. It started to differentiate, right, into layers based on density.
Right.
Yeah, we're talking about 3 main layers, and each one has a pretty unique composition. At the center, you've got this super dense core packed with iron, nickel, cobalt.
Very dense, about 10 to 15 grams per cubic centimeter.
Oh, wow. And that's surrounded by this thick sort of homogeneous mantle, less dense.
Around 4 to 6 GC-meter.
And then finally, on the very top, there's our thin, heterogeneous crust. It averages only about 2.8 grams per cubic centimeter. And that's where all life happens, right? And where we find most of the elements that are really critical to us.
Exactly. And these layers, they tell a kind of cosmic story, too. I mean, hydrogen and helium, they completely dominate the universe, but they're surprisingly rare here on Earth.
Why is that?
Well, they were mostly lost to space early on, too light to be held by Earth's gravity back when it was still forming and hot. So here on Earth, it's oxygen, silicon, iron, and magnesium that make up over 90% of the planet's total mass. But, crucially, it's in that thin crust, just, 0.4% of Earth's mass? That's where we find most of the non-metals, the metalloids, and those lighter, really active metals like aluminum, calcium, sodium, potassium.
Okay.
And this distribution, it all comes down to something called geochemical differentiation. When Earth was molten, gravity and chemical affinity basically sorted everything out. You got the iron-rich stuff sinking to the core, and then the lighter silicate and sulfide phases forming the mantle and crust.
Right, a massive sorting process.
Yeah.
But okay, this raises a really important question.
Yeah?
How did life, popping up on this relatively thin crust, manage to dramatically change its chemical composition? I think about the emergence of photosynthetic algae, those really early organisms. They started converting carbon dioxide and water into organic molecules. And the big thing was they released oxygen as a byproduct. And over hundreds of millions of years, this simple biological process utterly transformed our planet.
Yeah.
Led to an oxygen-rich atmosphere.
Oh, the consequences were immense, absolutely huge. This new oxidizing environment, it caused iron 2 minerals, the sort of thing stable in low oxygen conditions, to transform into iron minerals.
Yeah.
Like hematite, the reddish iron oxide. We see huge layers of it in ancient banded iron formations, evidence of this oxygenation event.
Wow.
And critically, the rise in oxygen also triggered an explosion of oxygen-utilizing life forms. That paved the way for us, for all the complex organisms we see today.
And it wasn't just oxygen, was it?
Yeah.
We also see things like plants absorbing potassium ions from the oceans, which actually contributed to the high sodium to potassium ratio we see in seawater today.
That's right.
Or think about the enormous deposits of buried organic carbon, basically ancient life, forming the coal and petroleum that, fuel our modern world. And even those vast sedimentary deposits of fossilized calcium carbonate limestone, marble hires, those are just the skeletal remains of countless tiny marine organisms piling up over millennia.
And what's also fascinating is how organisms fiddled with trace metals. Even though metals like manganese, copper, zinc, iron are pretty scarce in seawater, relatively speaking, many organisms evolved this incredible ability to concentrate them from trace amounts, sometimes increasing the concentration by 100, even 1,000 times compared to the surrounding water.
Really? Why?
It just highlights their absolutely essential biological roles. They're needed for enzymes, for all sorts of biochemical processes. It shows life's really profound influence on the chemistry of the crust.
Okay, so given these abundances and how life has shuffled things around, where do we actually get the elements we need today? I mean, some occur naturally, right? And they're an uncombined state, the native state.
Yep. Things like sulfur near volcanoes, or nearly pure carbon as coal, or the really unreactive metals like gold and platinum. You can find nuggets of them.
But most elements aren't like that. They're found in ores.
Right, exactly. Ores are natural compounds or mixtures from which we can extract an element economically.
That last part seems key. Economically.
It's always a critical consideration. Is it worth the cost of mining, processing, purifying? That determines if a rock is just a rock or if it's actually an ore. And you see patterns here too based on chemistry. Alkali metals like sodium and the halogens like chlorine, they're mostly found together in halides like rock salt, NaCl. Group 2A metals like calcium tend to occur as carbonates limestone, KCO3. Although magnesium is an exception, it's so abundant in seawater that we often just get it from there.
All right.
And then for most of the industrially important metals, the transition metals, they're found either as oxides, especially for metals on the left side of the transition series, or as sulfides, which are more common for metals on the right side, like copper or zinc.
And there's a chemical reason for that preference.
Absolutely. It's rooted in atomic properties, things like ionization energy and electronegativity, basically. How strongly an atom holds onto or attracts electrons. Metals with lower electronegativity tend to form more ionic bonds, making oxides very stable. Metals with higher electronegativity form more covalent bonds, which favors forming stable sulfides.
Got it. Okay, so elements aren't just sitting there, they're moving. The physical, chemical, and biological paths elements take through Earth's different regions, the air, the water, the land, they form what we call environmental cycles. Let's maybe look at three really essential ones, starting with carbon. Carbon seems to be everywhere.
It really is. Lithosphere rocks like graphite, diamond, carbonates, petroleum, hydrosphere dissolved CO2, all living matter. Atmosphere is gaseous CO2. And atmospheric CO2 acts as this crucial link, cycling between the oceans and the land. It takes about 300 years or so for a CO2 molecule to complete that cycle. Biological processes are absolutely central here. You've got photosynthesis.
Right, plants and plankton taking CO2 out of the air.
And fixing it into carbohydrates, sugars, and starches. Then you have respiration by animals and plants and decomposition by microbes, which release that CO2 back. And for millions of years, this natural cycle kept things pretty much in balance. Relatively constant atmospheric CO2, stable global temperature.
But here's where it gets really interesting and maybe a bit concerning. Over the past century and a half, human activity has just dramatically changed that balance. We're talking about burning fossil fuels, coal, oil, gas releasing huge amounts of stored carbon. Also, making cement from limestone releases CO2. And of course, deforestation reduces the number of trees pulling CO2 out of the air.
All adding CO2 to the atmosphere much faster than natural processes can remove it. And the consequences are, well, they're undeniable at this point. This sharp increase in atmospheric CO2 is unequivocally linked to global warming and climate change.
So you see it in the news all the time.
Absolutely. We're observing higher global average temperatures. The hottest years on record keep happening. We see altered rainfall patterns, more extreme weather, melting glaciers and polar ice caps, rising sea levels, and also increasing ocean acidity as the oceans absorb some of that excess CO2, which really impacts marine life, especially things with shells.
Yeah, it really raises that important question you mentioned. What responsibility do we bear in trying to address these pretty dramatic shifts in Earth's systems? Okay, moving on. Let's explore the nitrogen cycle next. You mentioned it's different from carbon because nitrogen compounds like nitrates are very soluble.
That's right. Unlike CO2, which has a significant gaseous reservoir, most nitrogen compounds are highly soluble in water. This means there's a direct land-to-sea interaction via runoff. Rain washes nitrogen compounds from the land into rivers and eventually the oceans. But the key challenge in the nitrogen cycle is fixation. The nitrogen in the air, N2 gas, makes up about 78% of our atmosphere, but it's incredibly stable. That triple bond between the nitrogen atoms is really strong.
So plants can't just use it directly from the air?
Nope. It has to be fixed, converted into a usable form like ammonia, NH3, or nitrates, NO3. This fixation requires a lot of energy. It happens naturally in a few ways. Atmospherically, during lightning strikes, which forms nitrogen oxides.
Wow, lightning.
Yeah, the intense energy breaks the N2 bond. Then there's industrial fixation, the Haber process, which makes ammonia for fertilizers, and crucially, biological fixation by certain bacteria, mostly in soil and root nodules. These microbes actually dwarf the other two processes in terms of the amount of nitrogen they fix globally.
Okay, but humans are adding a lot now, right, through industry.
A huge amount. Industrial fixation, mainly for agricultural fertilizers, has roughly doubled the amount of fixed nitrogen entering the environment each year compared to natural processes. Plus, high-temperature combustion in car engines and power plants also mimics lightning, breaking apart N2 and O2 in the air to form nitrogen oxides, which contribute to acid rain and smog.
And what are the consequences of all this extra fixed nitrogen?
The big one is eutrophication, when excess nitrogen from fertilizers and sewage runs off into lakes, rivers, and coastal areas.
Tax it a fertilizer there, too.
Exactly. It causes massive blooms of algae. When these algae die and decompose, the process consumes huge amounts of dissolved oxygen in the water. This oxygen depletion leads to the death of fish and other aquatic life, creating these dead zones. It's a serious problem in many waterways worldwide.
Right. Okay, our third cycle. Phosphorus. You said this one is unique.
It is. It's unique because it has essentially no gaseous component. There's no significant atmospheric involvement like with carbon or nitrogen. Phosphorus stays pretty much locked in the land and water systems. The phosphorus cycle really involves three interlocking subcycles operating on vastly different timescales. There's a very, very slow inorganic cycle. This takes millions of years. Phosphate rocks weather slowly, releasing phosphate into soil and water. It gets transported to the sea, incorporated into sediments, and eventually uplifted geologically to form new rock. Super slow.
Millions of years.
Yeah. But superimposed on that are much faster land-based and water-based biological cycles. These operate on timescales of years or even weeks. Organisms, plants, animals, microbes are crucial for rapidly cycling phosphorus through the biosphere.
And plants have adapted to get phosphorus, even though it might be scarce.
They have. Since many natural soil phosphates, like calcium phosphate, aren't very soluble, plants have evolved this clever trick. They secrete acids from their root tips. These acids help dissolve the insoluble phosphates, converting them into soluble forms like dihydrogen phosphate, H2PO4, which the roots can then absorb. But again, human activity dramatically alters this balance, just like with nitrogen. Our widespread use of soluble phosphate fertilizers in agriculture, and historically the use of phosphates as tripholyphosphates in detergents.
Oh yeah, I remember the push to remove phosphates from laundry detergent.
Exactly. Those sources effectively double the natural rate of phosphate input into rivers and lakes, and the result. Just like excess nitrogen, excess phosphorus causes massive eutrophication, widespread algal blooms, oxygen depletion, rendering rivers and lakes essentially dead and unusable. There's a famous historical example, Lake Zurich, back in 1912, I think. It was completely choked with algae due to sewage input. They eventually treated it by adding ferric chloride, FeCl3, which reacts with phosphate to form an insoluble precipitate, basically pulling the excess phosphate out of the water.
So we can sometimes intervene chemically to fix problems we cause?
Sometimes, yes, but preventing the pollution in the first place is obviously much better. It highlights how human impact can destabilize even these very slow-moving natural cycles.
Okay, that's a great overview of how elements occur and cycle. Now let's shift gears. How do we actually get these elements out of the ground and turn them into useful materials? This is metallurgy, right?
That's the science, yes. Metallurgy is the whole field focused on extracting metals from their ores and preparing them for use. Broadly speaking, there are three main approaches. There's pyrometallurgy, which relies heavily on high temperatures, pyro meaning fire. There's electrometallurgy, which uses electrochemical processes, basically electricity, to drive reactions. And there's hydrometallurgy, which uses chemistry in aqueous solutions, hydro meaning water. The choice depends entirely on the specific metal, its ore, and again, the economics.
And the basic steps are usually similar, regardless of the method.
Pretty much. You start by mining the ore, that mix of the valuable mineral and the worthless rock, the gangue. Then you usually need to pre-treat the ore to concentrate the mineral, getting rid of as much gangue as possible. After that, you often need to chemically convert the mineral into a form that's easier to reduce. Then comes the reduction step itself, getting the actual metal element from its compound. Then you typically need to refine the metal to get the desired purity. And finally, you might alloy it, mix it with other elements to get specific properties like strength or corrosion resistance.
Okay, let's break that down. Pre-treating the ore, concentrating it. You said it's like finding a needle in a haystack, but we have tricks.
We do several clever physical and chemical methods. For instance, if the mineral is magnetic, like magnetite F3O4, you can literally use magnets to pull it away from non-magnetic gangue.
Simple enough.
Or if there's a density difference, you can use techniques like cyclone separation. High-pressure air swirls the crushed ore. The lighter gangue particles get blown out, while the denser mineral particles fall down. Flotation is another really common one, especially for sulfide ores like copper ores.
How does that work?
You mix the crushed ore with water, oil, and a detergent. You bubble air through it. The mineral particles selectively stick to the oil-coated air bubbles and float to the top as a froth, which you skim off. The gangue doesn't stick, so it sinks.
Love it.
And then there's leaching, which is a hydrometallurgical approach. You use a chemical solution to selectively dissolve the desired mineral away from the gangue. A famous, or maybe infamous example is using a cyanide solution to leach gold. The gold forms a soluble complex ion, ACN2, which dissolves in the water, leaving the rock behind. Of course, cyanide is highly toxic, so managing that process safely is a huge environmental challenge.
Okay, so once the ore is concentrated, the next step is often converting the mineral chemically.
Often, yes. The goal is usually to convert it into an oxide, because oxides are generally the easiest form to reduce to the pure metal later on. So, for example, you might heat calcium carbonate, limestone, to drive off CO2 and leave calcium oxide, lime, that's called calcination. Or you might roast a sulfide ore, like zinc sulfide, ZNS, in air. The sulfur burns off as sulfur dioxide gas, SO2, leaving zinc oxide, ZNO.
Right. And then comes the reduction step, getting the actual metal. You mentioned carbon is common, smelting.
Yes, reduction using carbon, usually in the form of coke, which is derived from coal, is very common because carbon is cheap and effective. That whole process is called smelting. You heat the metal oxide with carbon at high temperatures. What's neat thermodynamically is that while the reaction might not be spontaneous at room temperature, at high temperatures, the carbon often forms carbon monoxide gas, CO.
Gas is key.
Yes, forming a gas dramatically increases the entropy, the disorder of the system. That makes the overall free energy change much more negative at high temperatures, driving the reaction forward. Often it's actually the CO gas produced that acts as the primary reducing agent, pulling oxygen off the metal oxide.
Okay, but carbon isn't always the answer.
No. Some metals react with carbon at high temperatures to form unwanted carbides, which can make the metal brittle. For those metals, like tungsten or germanium, hydrogen gas is often used as the reducing agent instead.
And if even hydrogen causes problems, like forming hydrides.
Then you might have to use an even more reactive metal as the reducing agent. A really spectacular example is the thermite reaction. You mix aluminum powder with chromium oxide, ignite it, and get this incredibly exothermic reaction, tons of heat and light producing molten chromium metal and aluminum oxide. Aluminum is acting as the reducing agent.
Wow, I think I've seen videos of that. Looks intense.
It is. Similar principles apply elsewhere too, like using zinc metal to reduce the gold cyanide complex back to solid gold in the leaching process.
Okay. And for nonmetals, it's the opposite, oxidation.
Exactly. To get a free nonmetal, like iodine from iodide ions in solution, you'd use a stronger oxidizing agent, perhaps chlorine gas, Cl2, to pull electrons away and form elemental iodine, I2. And finally, there's electrochemical reduction, which is crucial for very reactive metals. Here, you use electricity directly. You might electrolyze a molten salt of the metal, like molten beryllium chloride, BCl2, to produce pure beryllium metal at the cathode. The trick is often finding the right condition-specific electrode materials, maybe dissolving the compound in another molten salt, to make sure you get the metal you want and avoid unwanted side reactions, like electrolyzing water if it were present.
Okay, so we've extracted the metal, but you said it's usually not pure enough yet, so we're refining.
Right. Refining is all about purification. Several methods exist. Electrorefining is a really elegant one, especially important for copper. You set up an electrolytic cell where the impure metal acts as the anode, where oxidation happens, and a thin sheet of pure metal acts as the cathode, where reduction happens. As electricity flows, the impure metal dissolves from the anode and pure metal plates onto the cathode. The less reactive impurities, like silver, gold, platinum in the case of copper.
Valuable stuff.
Exactly. They don't dissolve, they just fall off the anode and collect at the bottom as a sludge called anode mud. Selling this anode mud can actually nearly offset the entire electricity cost of refining the copper.
That's amazing. What else?
Well, for metals with low boiling points, like zinc or mercury, you can use distillation, basically boil the metal off from less volatile impurities. And for achieving incredibly high purity, especially for semiconductors like silicon or germanium needed for electronics, there's zone refining.
How does that work?
You take a rod of the impure semiconductor. You pass a circular heating coil slowly along its length. The coil melts a small zone of the material. Impurities tend to be more soluble in the molten zone than in the solid, so as the coil moves, it drags the impurities along with the molten zone, concentrating them at one end of the rod, leaving the rest ultra-pure, sometimes better than 99.9999999% pure.
Incredible purity. And the final step you mentioned was alloying, mixing metals.
Yep. Alloying is simply mixing a metal with one or more other elements, which could be other metals or sometimes nonmetals like carbon, to get improved properties. Pure iron, for example, is relatively soft. Adding a small amount of carbon turns it into steel, which is much harder and stronger.
Right. Steel isn't an element.
Exactly. Brass is an alloy of copper and zinc. Bronze is copper and tin. Stainless steel adds chromium and nickel to iron for corrosion resistance. There are different types. In interstitial alloys, the added atoms are small enough, like carbon and steel, to fit into the gaps or interstices between the main metal atoms. In substitutional alloys, like zinc atoms replacing some copper atoms in brass, the added atoms are similar in size and just substitute for the host metal atoms in the crystal structure.
Okay, let's make this more concrete. Can we look at some specific elements and how we actually produce them industrially? Maybe start with those reactive alkali metals, sodium and potassium.
Sure. Sodium is mostly produced using the down cell. It's an electrometallurgical process. You electrolyze molten sodium chloride, NaCl, basically table salt, but NaCl melts at a really high 801 degrees C. To make it easier, they add calcium chloride, KCl2, which lowers the melting point down to around 580 degrees C. Saves a lot of energy.
That makes sense.
At the cathode, sodium ions are reduced to molten sodium metal, which is less dense than the molten salt, so it floats to the top and can be drawn off. At the anode, chloride ions are oxidized to chlorine gas, Cl2, which is itself a valuable industrial chemical.
And what's sodium metal used for?
One major use is as a coolant in certain types of nuclear reactors because it transfers heat very efficiently.
Okay, what about potassium? Similar process.
Actually, no. Potassium metal is too soluble in molten potassium chloride for simple electrolysis like the down cell to work well. So instead, its production relies on a clever bit of chemical equilibrium. They actually use sodium metal to reduce potassium ions, K+. Now, you might think sodium holds its electrons tighter, so why would it give them to potassium?
Yeah, that seems backwards.
It is at low temperatures, but they run the reaction at about 850 degrees C. That's above the boiling point of potassium, but below sodium's. So as potassium metal forms, it immediately turns into a gas.
And removing the product.
Exactly. By continuously removing the potassium gas, Le Chatelier's principle comes into play. The equilibrium is constantly shifted to the right, forcing more potassium to be produced to replace what's being removed. It's a really neat application of equilibrium principles.
And potassium uses.
One interesting use is potassium superoxide, KO2, in breathing masks for firefighters or miners. It reacts with exhaled CO2 and water vapor to release oxygen.
Cool. Okay, let's talk about the big three: iron, copper, and aluminum, the absolute backbone of industrial society. How do we get iron for steel?
Iron production is dominated by the blast furnace. It's a huge, continuous pyrometallurgical process. The reason smelting with coke is still used is primarily cost coke, made from coal, is relatively cheap fuel and reducing agent. You feed iron ore, usually oxides like hematite, Fe2O3, along with coke and limestone, CCO3, into the top of the furnace. Hot air is blasted in the bottom. The coke burns to produce heat and, crucially, carbon monoxide, CCO. It's actually the CO gas moving up the furnace that acts as the main reducing agent, stripping oxygen from the iron oxides at different temperature zones within the furnace.
And the limestone, what's that for?
The limestone acts as a flux. It decomposes in the heat to calcium oxide, CaO. This basic oxide reacts with acidic impurities in the ore, mainly silicon dioxide, sand, SiO2, to form a molten slag calcium silicate, KCO3.
So the slag removes the impurities.
Exactly. The molten slag is less dense than molten iron, so it floats on top and can be easily tapped off separately. The molten iron that collects at the bottom is called pig iron. It's still quite impure, containing about 3–4% carbon and other elements.
So pig iron isn't steel yet.
No. To make steel, the pig iron goes through another process, most commonly the basic oxygen process. Pure oxygen is blown through the molten pig iron. The oxygen reacts with the excess carbon, forming CO and CO2 gases, and oxidizes other impurities like silicon, phosphorus, manganese, and sulfur. These impurities form oxides, which then react with added fluxes to form another slag layer that's removed, leaving behind steel with a carefully controlled carbon content.
Okay, iron needs heat and carbon. What about copper? You mentioned its ores are often low grade.
Very much so. Ores like chalcopyrite, which is a copper iron sulfide Cu2, might only contain 0.5% copper, so concentration is vital. Yes, flotation is key to get the concentration up. Then it's a multi-step pyrometallurgical process. It involves controlled roasting in air to convert some of the iron sulfide to iron oxide while trying to leave the copper sulfide mostly untouched. Then heating with sand silica allows the iron oxide to react and form an iron silicate slag, removing the iron. Further heating and smelting converts the remaining copper sulfide, often C2S, into molten, impure copper metal, sometimes called blister copper.
But you said for wiring, it needs to be super pure.
That's the crucial step, electrorefining. Like we discussed, the impure blister copper becomes the anode. Pure copper plates onto the cathode, and you get that 99.99% purity needed for good electrical conductivity. And remember that valuable anode, mud, silver, gold, platinum falling off? That makes the whole energy-intensive refining process economically viable.
Right, and aluminum. The most abundant metal in the crust, but tricky to get.
Very tricky historically because aluminum is so reactive, it holds onto oxygen very tightly in its ore, primarily bauxite, which is hydrated aluminum oxide, Al2O3.NH2O. You can't just reduce it with carbon like iron. First, you need to purify the bauxite using the Bayer process. You treat the ore with hot, concentrated sodium hydroxide solution. Aluminum oxide is amphoteric.
Meaning it reacts with both acids and bases.
Exactly. So the aluminum oxide dissolves in the strong base, forming a soluble aluminate complex. Common impurities like iron thioxide and titanium dioxide don't dissolve, so they can be filtered off. Then you carefully change the conditions, like lowering the pH, to precipitate out pure aluminum hydroxide, LOH3, which is then heated strongly to get pure aluminum oxide, Al2O3, often called alumina.
Okay, pure alumina. Now, how do you get the aluminum out?
That requires the Hall-Héroult process, developed independently and simultaneously in the 1880s by chemists in the US and France. It's an electrometallurgical process. The key insight was finding something to dissolve the alumina because alumina itself melts at over 2,000 degrees C, which is impractically high. They discovered that molten cryolite, Na3AlF6, dissolves alumina quite well, allowing the electrolysis to run at a much more manageable 1,000 degrees C or so.
Still hot, but better than 2000.
Definitely. So you pass a massive electric current through this molten solution. Aluminum ions are reduced to molten aluminum metal at the cathode, often the carbon lining of the cell, which sinks and is tapped off. At the graphite anodes, oxide ions are oxidized, but they react with the hot carbon anode, forming carbon dioxide gas. So the anodes actually get consumed in the process and need periodic replacement.
And you mentioned the energy cost is huge.
Astronomical. Aluminum production accounts for something like 5% of the total electrical energy usage in the United States. It takes roughly 150 kilojoules of energy just to make the aluminum for one soft drink can via this primary production method.
Wow. Okay, that really raises the question. If it takes so much energy to make aluminum from scratch, what's the solution?
Recycling. Absolutely, recycling.
How much energy does that save?
It's dramatic. Recycling aluminum uses only about 5–7% of the energy required for the primary Hall-Héroult electrolysis. If you consider the entire energy input from mining the bauxite onwards, recycling uses less than 1% of the total energy.
Less than 1%.
Yes. It's an absolute economic and environmental no-brainer. That's why aluminum recycling programs are generally so successful.
And you also mentioned anodizing.
Right. That's a process often done to finished aluminum products. It's actually an electrolytic process that deliberately grows a thicker, more protective layer of aluminum oxide on the surface, enhancing its natural corrosion resistance and allowing it to be dyed various colors.
Okay, shifting from land to sea. Magnesium. You said we get it from seawater.
Primarily, yes, using the very clever Dow process. Seawater contains a fair amount of dissolved magnesium ions, Mg2+. First step is to precipitate these ions out. You add calcium hydroxide, TOH2, often called slaked lime. Where do you get that cheaply near the sea? From oyster shells, which are mostly calcium carbonate, you heat the shells to get calcium oxide, LARM, then react that with water to get calcium hydroxide.
So using seashells to get magnesium. Neat.
It is. The calcium hydroxide reacts with magnesium ions in the seawater to precipitate magnesium hydroxide, MgOH2, which is insoluble. This solid MgOH2 is filtered off, then reacted with hydrochloric acid, HCl, to form a concentrated solution of magnesium chloride, MgCl2.
Where does the HCl come from?
Cleverly, it's recycled from the final step. The concentrated MgCl2 solution is dried, melted, and then electrolyzed. Molten magnesium metal forms at the cathode, and chlorine gas forms at the anode. That chlorine gas is reacted with hydrogen, often produced on site too, to regenerate the HCl needed earlier in the process. Very efficient cycle.
And magnesium uses.
It's the lightest structural metal, so it's used in alloys for things where weight is critical aircraft parts, high-performance cars, camera bodies, laptops. It's also used as a reducing agent itself to produce other reactive metals, like titanium.
Okay, one more element. Hydrogen. Most abundant in the universe, but rare as H2 gas here.
That's right. On Earth, almost all hydrogen is locked up in compounds, primarily water, H2O, and hydrocarbons like methane, CH4, in natural gas. Producing pure H2 gas industrially requires significant energy input. There are two main routes. Where electricity is cheap, especially from hydroelectric power like in Scandinavia, electrolysis of water is used. You pass electricity through water, usually with an electrolyte added to conduct current, splitting it into very pure hydrogen gas at the cathode and oxygen gas at the anode.
Simple H2O splitting.
Conceptually simple, yes, but energy intensive. The other major route, common where natural gas is abundant, like in the US, involves thermal methods. The main one is steam reforming of methane. Methane reacts with high-temperature steam over a catalyst to produce carbon monoxide and hydrogen. Often, this is followed by the water-gas shift reaction, where the carbon monoxide reacts with more steam to produce carbon dioxide and even more hydrogen. The CO2 can then be removed, leaving relatively pure hydrogen.
And what do we use all this industrial hydrogen for?
A huge amount goes into making ammonia, NH3, via the Haber-Bosch process, mostly for fertilizers. Another major use is hydrogenation of vegetable oils. Reacting them with hydrogen over a catalyst turns liquid oils into solid or semi-solid fats, like margarine. It's also used to produce methanol, CH3OH, an important industrial solvent and feedstock. And of course, there's a lot of interest in hydrogen as a potential clean fuel for fuel cells in the future, though there are challenges with storage and infrastructure. And a quick related point. Deuterium, the heavier isotope of hydrogen, often written as D or 2H, we can actually produce heavy water, D2O. It relies on the kinetic isotope effect. Bonds involving lighter isotopes tend to break slightly faster than bonds involving heavier isotopes. So during the electrolysis of water, the OH bonds in H2O break a tiny bit faster than the OD bonds in HDO, which is always present in natural water. This means H2 gas is produced slightly preferentially over HD or D2 gas. If you electrolyze large amounts of water, the remaining water becomes gradually enriched in D2O. It's a slow, energy-intensive process, but it allows for the production of heavy water, which is used in certain types of nuclear reactors as a moderator.
Fascinating how subtle differences in atomic mass can be exploited.
Okay.
Let's wrap up with two really foundational chemical manufacturing processes: sulfuric acid and the Chlor-Alkali process.
Absolutely foundational. Sulfuric acid, H2SO4, is often called the king of chemicals, or the most important chemical just based on sheer volume. Something like 290 million tons produced globally each year. It's used everywhere: fertilizers, pigments, plastics, refining metals.
How is it made?
Almost entirely by the contact process. It's a multi-step process that's remarkably efficient. Step 1. Get sulfur. This might come from mining native sulfur deposits, using the Frash process, which bumps superheated water underground to melt the sulfur, or increasingly by recovering hydrogen sulfide, H2S, from natural gas and oil refining, using the Claus process, and converting that to sulfur. Step 2. Burn the sulfur in air to produce sulfur dioxide gas, SO2, simple combustion. Step 3. This is the crucial contact step. Oxidize the SO2 to sulfur trioxide, SO3, using air. This reaction is slow, so it requires a catalyst, usually vanadium V oxide, V2O5.
And there's an equilibrium challenge here.
Yes. The reaction SO2 plus half O2HO3 is exothermic, meaning it releases heat. According to Le Chatelier's principle, lower temperatures favor higher yield, push the equilibrium to the right. But lower temperatures also mean a much slower reaction rate.
The classic kinetics versus thermodynamics trade-off.
Exactly. The V2O5 catalyst is key because it allows the reaction to proceed at a reasonable rate at moderately high temperatures, around 450 degrees C, that still give a decent equilibrium yield. They also use excess oxygen and remove the SO3 as it forms to further push the equilibrium towards products. Step 4. Convert the SO3 to H2SO4. Now you might think just bubble SO3 through water, right? SO3 plus H2O H2SO4. Turns out that reaction is too vigorous. It creates a persistent acidic fog or mist that's hard to handle and results in low yield. So instead, they absorb the SO3 gas into existing concentrated sulfuric acid. This forms an intermediate called pyrosulfuric acid, H2S2O7, also called oleum. Then they carefully add water to the oleum to produce the desired concentration of sulfuric acid. It's a safer, more efficient indirect route.
And you said it's remarkably inexpensive.
It is, partly because all the main reaction steps, burning S, oxidizing SO2, are exothermic. Modern sulfuric acid plants are designed to capture this released heat and use it, often selling it as steam to nearby factories or using it to generate electricity, which significantly offsets the production cost.
Very efficient. Okay, finally, the chlor-alkali process. Sounds important.
It is another cornerstone of the chemical industry. It's the electrolysis of concentrated aqueous sodium chloride brine to produce three vital chemicals simultaneously: chlorine gas, Cl2, hydrogen gas, H2, and sodium hydroxide, NaOH, also known as caustic soda.
How does that work? You're electrolyzing salt water?
Essentially, yes. At the anode, chloride ions are oxidized to chlorine gas. At the cathode, water molecules are reduced to hydrogen gas and hydroxide ions. The sodium ions, Na+, are spectator ions in solution, but they combine with the hydroxide ions produced at the cathode to form the sodium hydroxide solution. Now, chemically, you might expect water to be oxidized at the anode before chloride ions based on standard potentials. But due to a phenomenon called overvoltage, basically an extra voltage needed to make a reaction happen at a reasonable rate on certain electrode surfaces, the oxidation of chloride happens preferentially when using specific anodes and concentrated brine.
And there have been different ways to do this industrially.
Yes, the technology has evolved significantly, driven by efficiency and environmental concerns. The oldest large-scale method was the diaphragm cell method. It used a porous diaphragm, often made of asbestos, to separate the anode and cathode compartments. This prevented the chlorine produced at the anode from reacting with the sodium hydroxide produced at the cathode, but it allowed ions to migrate, resulting in NaOH solution that was still contaminated with some unreacted NaCl, industrial grade but not super pure. Then came the mercury cell method. This used a flowing pool of liquid mercury as the cathode. Mercury has a very high overvoltage for reducing water, so instead of water being reduced, sodium ions, Na+, are actually reduced and dissolve in the mercury to form a sodium-mercury amalgam, NaHG.
So you get sodium metal dissolved in mercury.
Exactly. This amalgam then flows into a separate compartment where it reacts with pure water to produce very high-purity sodium hydroxide and hydrogen gas, regenerating the mercury, which is pumped back to the electrolytic cell.
It sounds clever, but...
Mercury. That's the huge downside. Despite efforts to contain it, significant amounts of mercury were inevitably lost to the environment, maybe 200 grams of mercury per ton of chlorine produced. This led to serious pollution problems, like in Minamata Bay in Japan. So the mercury cell process is being phased out globally due to environmental regulations.
Good. So what's used now?
The state-of-the-art is the membrane cell method. This replaces the asbestos diaphragm or the mercury cathode with a special polymeric ion exchange membrane. This membrane is designed to allow only positive ions, cations like Na+, to pass through from the anode compartment to the cathode compartment, while blocking negative ions, anions like Cl and OH, and the gases. This allows for the production of very pure, concentrated sodium hydroxide directly at the cathode, uses less electricity than the older methods, and crucially, completely eliminates the mercury pollution problem. It's a much cleaner, more efficient technology and represents the future of the chlor-alkali industry. It's really a prime example of chemical engineering responding to environmental needs.
That's a great example. Okay, so let's try to wrap this all up. What does this all mean? We've really journeyed from, like, the molten core of the early Earth through the intricate dance of element cycling in our environment, the air, water, land, and finally, we've seen the incredible feats of chemistry and engineering that transform these raw materials into the essential products that, well, define our modern world. Hopefully you feel like you've gained a truly comprehensive understanding of these elements in nature and industry.
I hope so too. I think the key thing to remember is that Earth's chemistry isn't static. It's this incredibly dynamic system. It's been profoundly shaped over billions of years by geological forces, but also, crucially, by living organisms. And human ingenuity, guided by those core chemical principles, kinetics, equilibrium, thermodynamics, electrochemistry, allows us to tap into these vast resources. But as we've seen repeatedly, this power comes with significant responsibilities. We see the impacts on the carbon, nitrogen, and phosphorus cycles. This drives the need for greater efficiency, for sustainability, like we saw with aluminum recycling, or the move away from mercury cells in the Chlor-Alkali process.
Right. So maybe a final thought for everyone listening is, as you look around you today, just consider the elements in everything you see, the device you're listening on, the chair you're sitting in, the building you're in. What other treasure, maybe not gold, but what other useful substance or efficient process lies undiscovered or unoptimized in our natural world, just waiting for the next chemical innovation? Thank you so much for joining us on this deep dive. This has been a presentation from the Last Minute Lecture team. We really hope you feel more informed and maybe even more curious about the amazing chemistry that underpins our lives.